Until now we have been dealing with individual single random variables and their properties such as their probability mass function, their cumulative distribution function, expectation, variance and so on. However, in several practical problems what you will be faced with is you want to analyze multiple random variables simultaneously. What are the key tools for doing that? We will look at that in this lecture. The first tool is the most basic tool, which is you generalize the probability mass function of individual random variables to multiple random variables. Let us take the simple case of 2 random variables, let us say x and y are 2 random variables from omega to r. The joint probability mass function of this pair of random variables x and y is denoted by small f subscript xy, and small fxy of x comma y is simply the probability of x equal to x and y equal to y. In terms of events, this means the probability of the set omega in the sample space such that x of omega equal to x, and which is denoted by intersection set of omega in omega such that y of omega equal to y. So, as this is a valid event and this is a valid event, so intersection of events is also valid, and so the probability of this is a valid probability measure. So, that is what we mean by probability of x equal to x and probability of y equal to y. This generalizes the probability mass function to multiple random variables. Easily it also generalizes to 3 or 4 or 5 or any number of random variables. Similarly, you can also have a cumulative distribution function, which is capital F xy of x comma y, which is simply the probability of x less than or equal to x and y less than or equal to y. So, this generalizes the cumulative distribution function of single random variables to multiple random variables. Let us take a look at a simple example to make these ideas concrete. Let us consider the standard double dice throw experiment with the counting probability measure, which corresponds to using both the dice being fair. Let us take the 2 random variables, x being the result of the first dice and y being the absolute value of the difference between the 2 dice. We have individually analyzed both these random variables and we know their probability mass function, expectation and so on, but we have not analyzed them together till now. Let us do that. We know that the result of the first die can take values between 1 to 6 and the absolute value of the difference can take values between 0 to 5. So, the probability mass function, to know the probability mass function you need to know this entire table. So, how do you interpret this table? For example, this number here corresponds to the probability of x equal to 1 and y equal to 0. So, what is that? Well, x equal to 1 means that the result of the first die is 1 and the absolute value is 0 means that the second die also has to be 1. Right? So, that is exactly equal to 1 by 36. 1 comma 1 is the only event, that only outcome that results in this. So, that is 1 by 36. Similarly, you can fill in the entire first row would be 1 by 36 all throughout. The second row is a little bit more interesting. Let us say the first die roll is 2. What is the probability the first die roll is 2 and the difference is 0. So, the only outcome for this is 2 comma 2, which is 1 by 36. But the absolute difference being 1 means that both 2 comma 1 and 2 comma 3 are valid outcomes which result in this particular configuration of x being 2 and y being 1. So, the probability of this event is 2 by 36, and similarly you can fill in this entire row here. Note that probability of x equal to 2 and y equal to 5 is 0. If the first die roll is 2, there is no way the difference can be 5. Similarly, you can fill in rows 3, 4, 5 and 6 and so on, and a key thing to note is if you added the entire table, that should exactly correspond to 1. Why is that? Well, for the exact same reason, the probability mass function should sum to 1. The joint probability mass function should also sum to 1. Why is that? Well, sum over x comma y fxy of x comma y is exactly equal to sum over x comma y probability of x of omega equal to x and y of omega equal to y. These sets are disjoint and their union corresponds to the entire sample space. So, which is equal to probability of omega, which is equal to 1, right. So, that is the reason why this entire table should sum to 1, and as a quick check you can see that does indeed happen. So, that this is a pretty simple example for doing joint distributions. This is called a joint mass function or a joint distribution. So, there are a couple of derived distributions from the joint distribution, which are the marginal and the conditional. The marginal is something which you have already seen, which is simply the PMF of the individual random variables. What is fx? What can you say about fx of x? Well, fx of x is simply the probability of x equal to x, right, which is simply the union over all y, probability of x equal to x and y equal to y, which is equal to sum over y in range of y fxy of x comma y. So, you sum over y, you sum the joint over y, you get the marginal over x. Similarly, you can have f y of y is sum over x in range of x fxy of x comma y. By marginalizing or summing out over x, you get the marginal distribution over y, and similarly by summing over y you get the marginal distribution over x. This is pretty simple and straightforward. Then you have a couple of other derived distributions, which are the conditional distributions. Fx given y of x given y is simply the probability of x equal to x given y equal to y. X equal to x is an event and y equal to y is also an event. So, this is a valid probability statement, right. So, we can have the left hand side, both these are events. So, we already know conditional probability of events, this is the definition. But we can go further and say probability of x equal to x given y equal to y is simply probability of x equal to x and y equal to y by probability of y equal to y, which is exactly equal to fxy of x comma y by fy of y. Similarly, you can have fy given x of y given x, which is fxy of x comma y by fx of x. We will illustrate these distributions also for the same example we had. Let us take the double dice throw experiment with x being the first phase and y being the absolute difference. We already have the marginal distribution. We can compute, we already have the joint distribution. We can compute the marginals just by summing over the rows or columns. To get the marginal distribution fx, you just sum over the columns, right. You get each row sum corresponds to fx, and the sum over the first row you get 1 by 6. Sum over the second row you get 1 by 6 and so on, and you can see that fx ends up being 1 by 6, which you already know, right. The probability mass function of the first phase is exactly equal to this, you know that. And by summing over the column, each column sum corresponds to a marginal distribution fy of y. So, summing over the first column corresponds to the probability of y equal to y, which is 6 by 36, for probability of y equal to 0, which is 6 by 36, and similarly summing over the second column gives you probability of y equal to 1, which is 10 by 36 and so on. This is also known, we computed the probability mass function of the random variable y previously, and you can see this matches the previously computed probability mass function of y. So, this is the marginal fx and this is the marginal fy and the joint fxy. Now we will try to get the conditional distributions. So, the conditional distributions, let us do fx given y, right. Let us have the same example, x being the first phase, y being the absolute difference. We are now interested in finding the conditional distribution fx given y of x given y. What does this mean? This means that the probability of x equal to x given y equal to y, right, which means that if you sum over all x for any given y, you should get 1, right. You sum over x fx given y of x given y should be equal to 1. Whatever be the value of y, y is given, right. So, you sum over all values of x, you should get back 1, right. So, that is the first clue, and based on that we know that fx given y is simply the joint divided by the marginal fy, which essentially corresponds to taking each column and dividing that by its sum. So, if you do that, you get 1 by, take this column 1 and divide that by 6 by 36, you get 1 by 6. Let us take the second column and divide that by Fy. So, this is you get 1 by 10, 2 by 10, 2 by 10, 2 by 10, 2 by 10 and 1 by 10. Similarly, you can do that for the third column also. You get 1 by 8, 1 by 8, 2 by 8, 2 by 8, 1 by 8, 1 by 8. Where is the 8 coming from? The 8 is coming from the column sum. Sorry. Similarly, you can do that for the fourth column. You will get 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6. And the fifth column we get 1 by 36. So, 1 by 4, 1 by 4, 0, 0, 1 by 4, 1 by 4. Finally, the last column you get half and half for. Let us try to interpret this. For example, let us try to interpret the last column. What does it say? It says that the probability of x is equal to 1, that is the probability of first phase being 1 is equal to half when the difference is 5, or the probability of first phase being 6 when the difference is 5 is half. So, that means that when difference is 5, x, the first phase is either 1 or 6 with equal probability. That makes sense to us, right. So, when the difference between, when we know that the difference between the two, absolute difference between the two die throws is 5, well, the first throw bet should either be 1 or 6. That is the only two possibilities and both are equally likely. That is what this is capturing. And similarly, you can see that each column clearly sums to 1. So, this is the conditional distribution Fx given y. And you can do a very similar thing for conditional Fy given x. The only difference is that you would take the joint and take each row and divide that by its row sum. So, that way you get Fy given x. You can interpret this in the exact same way. This is an exercise for you to do in your home. Right. Now, we will move to another important concept, which is independent random variables. We have already seen independent events. We will say two events A and B are independent if probability of A intersection B is equal to probability of A into probability of B. Right. So, that is the that is for independent events. But what does it mean to say two random variables are independent? A very similar definition goes here, that is, we will say two random variables x and y from omega to r are independent if the joint distribution fxy of x comma y is equal to fx of x into fy of y. There are several equivalent ways to get this. One is to say that for all values a and b, the events given by x equal to a and y equal to b are independent. Note that x and y are random variables, but for some constants a and b, if you say x equal to a, that is an event. So, independent, how are independent random variables and independent events related? Because we are using the same term here, that is because you can convert you can define independent random variables in terms of independent events as follows. So, the equivalence between these two is pretty easy to show, but there is also one other equivalent statement that you can say, which is that the expected value of f of x into g of y is equal to expected value of, let us not use f, let us use g and h. Expected value of g of x into expected value of h of y. for this holds for all functions g and h. You take any function g and h, then the expected value of the product of g of x into h of y is simply expected value of g of x into expected value of h of y. So, this is an equivalent definition for independence. We will actually prove you go from here to here, we will prove one direction, the other direction is just as easy actually. So, we will just prove this direction here. What is expected value of g of x into h of y? So, in this case there are two random variables x and y. So, expected value of g of x into h of y is simply given by sum over x comma y fxy of x comma y into g of x into g of x into h of y. But we know that if the random variables x and y are independent, this is exactly equal to sum over x comma y fx of x into fy of y into g of x into h of y. And by simple distributive law you can write this as sum over x fx of x into g of x into sum over y fy of y into h of y. This is exactly equal to the expected value of g of x and into expected value of h of y. So, this is a pretty easy proof and follows naturally from the definition of independent random variables. Independent random variables are actually one of the main basis from which you build more complicated dependencies. One useful interpretation is that if two random variables are independent, one random variable contains absolutely no information about the other. Knowing the value of one random variable gives you absolutely nothing about the other. For example, the classic example would be, let us say you have two dice that you are throwing, the double dice throw experiment with the standard probability measure, counting probability measure, which corresponds to probability of any event A is cardinality of A by 36. So, for that case where which is equivalent to having two independent two fair dice, let us say the first random variable is the x is the first phase for the first die result and y is the second die result. You can clearly see that these two are independent random, naturally it seems that they are independent random variables and that does reflect in the joint distribution. So, you can have let us say x and y can take values 1, 2, 3, 4, 5 and 6. Similarly, y also can take values 1, 2, 3, 4, 5 and 6. So, you can fill in each cell in the entry here what is the probability that x is equal to 1 and let us say y equal to 1, that is 1 by 36. In fact, the entire table is going to be filled with 1 by 36. Right, this entire table is going to be filled with 1 by 36. And you can compute the marginals of x and y by row sums and column sums, which is 1 by 6, 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 1 by 6. You can clearly see that to get any cell you can just multiply by the row sum and column sum, you get back that number. So, fx of x comma y is exactly equal to fx of x into fy of y. So, this forms a pair of independent random variables x comma y are independent. And the intuitive idea that x gives no information about y is obvious, right. So, if you know that the first die was 2, that does not help you in any way in finding out what the second die was. Here is the example that we did first, it is the same double dice throw experiment where x is the first phase and y is the absolute difference. Here you can clearly see that fx of x comma y is not equal to fx of x into fy of y. For example, here you have 0. 4 by 36 times 1 by 6 is clearly not 0. Right. So, you have fx of x comma y is not equal to fx of x into fy of y, and because x and y are not independent. Why is that, and how does x give, say, let us say some information about y? Let us take the case where let us say x is equal to 3. If you know x equal to 3, which is the first phase is 3, you know for certain that the difference cannot be 5, right, you know for certain. So, that is some information. Based on the knowledge of x, y can give you some information. Based on knowledge of x, you do get some information about y, right? You do get some information about y. So, that is the reason why x and y are not independent in this case. Okay, right. So, we will move on to the next topic, which is sum of independent random variables. So, we will not go into great detail about this topic. So, let us say you have 2 independent random variables x and y from omega to r. Let us say you have another random variable z, which is x plus y. You want to know the probability mass function of z from the probability mass function of x and y. How do you go about doing that? Well, fz of z is equal to probability of z equal to z. When can z be equal to z? When, well, for any value of x, when y equal to z minus x, you get that, right. So, when probability of x equal to x and y equal to z minus x, and this is true for any value of x. So, you have to sum over x. So, this is sum over x, probability of x equal to x, y equal to z minus x, which by our notation of the joint probability mass function, the sum over x fxy of x comma z minus x. And because we assumed x and y are independent, you can write fxy as fx into fy. So, which means that it is sum over x fx of x into fy of z minus x. You can, this is called a convolution operation, and here is a simple exercise. Let us take the double dice throw experiment where x is the first result of the first die throw, y is the result of the second die throw, and get these two are clearly independent. Use the convolution theorem to get the probability mass function of the sum of the two die throws. You know the answer anyway already, but use the convolution theorem to get the answer here. Okay. All right. We will move on to the next topic, which is conditional expectation. Right. So, we have already defined conditional expectation conditioned on an event, right. So, we have a random variable x from omega to r, and let us say a is a subset of omega. We have already defined expected value of x given a, we have defined that. But let us say you have another random variable y from omega to r. What does it mean to say expected value of x given y? First of all, you can't directly use this statement because the expected value of x given a is defined only for a being events, y is not an event, y is a random variable. But there is always the standard way to convert a random variable to an event is to assign a value to it, right. So, that is the but if you assign different values to it, you get different events, and based on that the answer expected value of x given a is going to change. So, expected value of x given y can be viewed as a function of y. As a function of y. Y is a random variable, but it can be viewed as a function of y. Let us take a very simple example, and that should make a lot of things clear. That is, let us say x is the sum of die throws. Let us say in the double die throw experiment, sum of die throws, and y is the first die throw. What is the expected value of the sum given the first die throw is y, right. In this case, you know it is exactly equal to, that means that you are taking the second the first die throw as a constant. So, that means that expected value of x given y is exactly equal to y plus the expected value of the second die throw, which you know happens to be 3.5. You can see that expected value of x given y is a function of y. So, this is still a random variable, but it is a function of y, that is the key thing to note here. We will use the conditional expectation in this term, in this form quite often in the next machine learning course, but right now this is sufficient to know that conditional expectation, expected value of x given y, is a function of the random variable y. Finally, we will move on to the next topic, which is covariance. Let us say you have two random variables x and y from omega to r. Okay. So, what is the covariance of the two random variables x and y? The formal definition of the covariance is the expected value of this particular object x minus Ex into y minus Ey. X minus Ex and y minus this entire thing can be viewed as a random variable. So, expectation of this random variable, that is, it is a perfectly valid way, definition here. In particular, if you have covariance of x comma x, you get back the variance of x. So, what is the interpretation of the covariance of a random variable? If you have the covariance of two random variables as high and positive, that indicates that these two random variables generally go together, either increase together or decrease together. For example, you might hear in some statistical study saying that the covariance between heart risk and blood pressure is positive, which means that as your blood pressure increases, your heart risk also increases. You can also be negative. For example, you can say the covariance between your, let us say, exercise, number of hours you put into exercise and heart risk is negatively correlated. You can hear a statement like this, which means that as you exercise more, your heart risk decreases. Right? So, that means that it is a negative correlation. Covariance can also be 0, and that special case is called uncorrelated. So, if covariance of x comma y equal to 0, this particular pair of random variables are said to be uncorrelated. And yeah, now let us actually do this expectation and simplify this. Right? Covariance of x comma y is expected value of x minus Ex into y minus Ey. Simplifying this further, expected value of, we will just do the product inside, which is expected value of xy minus Ex into y minus x into Ey plus Ex Ey. Ideally, after every E I should put a square brackets, but I am taking it to be implicit. When I say Ey, I mean E square brackets within square brackets y. Let us use the linearity of expectation to go further. So, this is expected value of xy minus expected value of x. You can, Ex is a constant, so you can take this out. So, this becomes Ex into Ey. Similarly, you have minus Ex into Ey plus Ex into Ey. Together you get Exy minus Ex into Ey. This would be another definition of covariance you might see, and you can see that if x is equal to y, you get back the old definition of variance, which is Ex squared minus Ex the whole squared. This should immediately tell you one thing, which is from our definition of independent random variables. We showed that if you have independent random variables x and y, expected value of product is equal to the product of expectation. So, which means that if x and y are independent, then this implies expected value of xy is equal to expected value of x into expected value of y, which is equivalent to saying that covariance of x comma y equal to 0. So, this is our first statement, that is if x and y are independent, then they are uncorrelated. But this does not flow this direction. You can have two random variables which are uncorrelated, their covariance can be 0, but they can still be dependent. Right. We will see a quick example of this. Right. Before we see an example of that, let us see a simple example of something which we know to be independent. Right. Let us take x to be the, let us take the double coin toss experiment. Let us take the double coin toss experiment where your sample space omega is simply HH, HT, TH and TT. Right. And let us take the two random variables which are independent. Let us say x is equal to the indicator of first toss is heads. Which means that we know exactly what this means. Let us say y is the indicator of second toss is tails. X and y are independent. Why is that? Well, we can write down fx of x. Fx of x is equal to half if x equal to 0, half x equal to 1. What is fy of y? Similarly, fy of y is also equal to half if x equal to, if y equal to 0, half if y equal to 1. What is the joint? Well, fxy of x comma y equal to 1 by 4 if x equal to x belongs to 0 comma 1 or y belongs to 0 comma 1, right. So clearly you can see that fx of x into fy of y is equal to fxy of x comma y. So x and y are independent. So in this case x and y also happen to be uncorrelated. So this is a simple example of pair of independent random variables which are also uncorrelated. Why is that? Well, what is Ex? What is Ey? Ex is equal to half and Ey is also equal to half. What is Exy? Well, when is xy equal to 1? Xy is equal to 1 when exactly when first coin toss is heads and the second toss is tails. Every other situation it is going to be equal to 0. So this the probability of xy is equal to 1 is equal to 1 by 4, which means that expected value of xy is equal to 1 by 4, which is exactly equal to Ex into Ey. So you have x and y are independent and you also check that they are uncorrelated. Right. Let us take another example where you have a situation where you have uncorrelated random variables, but they are actually dependent. Right. Let us say you have x and y. I will actually directly give the joint x and y are defined as follows, which is fxy of x comma y is given by this table. Let us actually just directly give the table, say -1, 0, 1, -1, 0, 1. X and y take the values -1, 0 and 1. Right. The joint distribution function is given by this table. You can clearly see that this sums to 1. So, this is a valid probability mass, joint probability mass function. What is Ex? Well, we can compute the marginal probabilities Fx and Fy. So, if you did the marginal probabilities you would get 3 by 8, 2 by 8, 3 by 8 and similarly you get 3 by 8, 2 by 8, 3 by 8. Right. So, what is Ex and what is Ey? Well, Ex is probability of x equal to -1 is 3 by 8, probability of x equal to 0 is 2 by 8, probability of x equal to 1 is 3 by 8. So, clearly Ex equal to 0. Similarly, Ey is also equal to 0. Right. What is Exy? Xy can take values either 1, 0 or -1, right. So, x can take values -1, 0, 1, y can take values -1, 0, 1. So, xy can also take values 1, 0 or -1. What is the probability that xy is equal to 1? Well, that can happen when x is equal to 1 and y equal to 1, or x equal to minus 1 and y equal to minus 1. So, which corresponds to these two numbers, which is minus 1 by 8 plus 1 by 8, that is 1 by 4. Similarly, probability of x y equal to 1 is equal to 1 by 4, probability of x y is equal to minus 1 is equal to 1 by 4, and probability of x y equal to 0 is half, right. So, clearly EXY is also equal to 0. So, EX equal to 0, EY equal to 0, and EXY is also equal to 0. So, this is clearly an uncorrelated pair of random variables. But are they independent? You can clearly see they are not independent. Why is that? Because you have a 0 here, fxy of 0 comma 0 is 0, but fx of 0 and fy of 0 are 2 by 8 and 2 by 8. So, if they were independent, you would have had here 2 by 8 and 2 by 8 and not 0. So, even though these two random variables are not independent, they are uncorrelated. We can see that Ex into Ey is equal to Exy. So, the covariance of x and y happens to be 0. So, this is a pair of uncorrelated covariance of x comma y equal to 0, but not independent. Right. So, with that we wrap up this introduction to multiple random variables. In the next lecture we will take a look at specific example named random variables and their probability mass function, their CDF and some properties.